So this second example of two-dimensional projectiles in the average velocity table looks very similar to the last one, but we'll note that it's kicked at an angle of 30 degrees at 18 meters per second at the top of a 100-meter cliff. So we can see is that there is this initial part of the motion that would be the same as what we did in the previous example. However, we'll need to add on a second part to it. So we've got our initial height of the starting position of 0. We've got a cliff whose position at the bottom is minus 100. We've got this going on, and it's that part that we did in the previous example, and now there'll be this additional part like so that we're adding on. So what I did here is I redid the table. It's basically the same numbers, but instead of writing out 15.58, we rounded it to 16, and we filled in all the other numbers up to what we had done last time. So now what we're looking for when this thing hits the ground is we're looking for the position Z, the vertical position, to be minus 100. So how far we fill out this table is really going to be dictated by that minus 100. So we're going to continue to fill it out across the board, and that way we don't do more work than is necessary. So after 3 seconds, 16. VZ is changing by 10. So that becomes minus 21. The average velocity in the Z becomes minus 6. And again, that's minus 21 plus 9 is minus 12. Minus 12 divided by 2 is minus 6. And the horizontal distance is 48. And our vertical distance is minus 6 times 3, which is minus 18. Going back to the next row, we're probably going to have to do at least 2 more rows, so let's do 2 more. 16, 16. And the green is changing by 10. The vertical, minus 31, minus 41. The VZ is changing by minus 5, so minus 11 and minus 16. And our horizontal displacement is going to be 64 and 72. And the vertical displacement is going to be 11 times, minus 11 times 4 is minus 44. And minus 16 times 5 is going to be minus 80. So we're still not there. We can see here in this last one, we changed by 36. So it's going to change by more than that this next time, which will take us to beyond minus 100. So we only need one more. So 16 minus 51 minus 21 and 88. We made a mistake here before. It wasn't 18s, it was 16s. So this is 80 and this is 96. And the green is minus 21 times 6, which is minus 126. So 100 is closer than the halfway point in terms of distance. And so it might be right about the halfway mark because it's traveling faster in the second half. So we might estimate 5.5, and we're not going to be off by more than maybe 0.2 if we do that. So say the impact is about 5.5. We'll have this will be 16. This here we'll say it's 46 minus 46. And this horizontal distance here will be about 88, and the vertical then would be about minus 100. So we've got estimates for let's see if we have which things we can give estimates for. How long will it take to hit the ground? We've got that estimate. That's about 5.5. How far will it be from the base of the cliff? We think that'll be about 88 meters. What will its horizontal and vertical velocities be? Well, we think that the Vx will be, we know it'll be 16, and the Vz will be about minus 46. And what will its impact velocity be? So we've got to draw this out this time to figure this out because we're not dealing with a purely symmetrical situation anymore. So in the beginning, we had our 16 meters per second, our plus 9 meters per second for the 18 meters per second overall. And when we got back to the same height, we had 16 meters per second and minus 9 meters per second. So we had 16 meters per second, minus 9 meters per second, and then overall at 18 meters per second. But then it's down near the ground upon impact, and we still have the same 16 meters per second. But upon impact, we now have a vertical velocity of minus 46 meters per second. So we can see this side is more than 3 times longer than the other. So using Pythagorean theorem, we can find the hypotenuse, and we can also find this angle here. This angle theta will be the same as this angle theta. Now let's call it phi because it's going to be different than the launch angle theta, which was 30. So call it angle phi. And so in that case, we've got tangent. So the tangent of phi is opposite over adjacent. This is our opposite side, and this is our adjacent side. So then theta is the inverse tangent of 46 over 16. So after plugging those into Desmos, we find out that C is 48.7. 0.70 meters per second, so 48.70, and that's what we'd expect. It's got to be bigger than 46. And the angle phi is 70.8 degrees, which we might expect because it's pretty steep. So, of course, two significant digits, that's going to be 49, and that's going to be 71 degrees in that case. So going back up to our angles, what will its impact velocity be? It will be 49 meters per second and at about 71 degrees to the horizontal. So that's how we could use the table to get an estimate of these things. And of course, you can see here the way we've drawn it, that looks like a pretty big angle, and that's the 71 degrees. So now how do we go about doing an analytic solution? Just the way we did the previous problem. We set up a system of equations for both dimensions, x and z. So for our x, we have Vx equals AT plus V0. The acceleration horizontally is 0, and so we just have this 15.58. Now, so since we are looking for analytic, we're going to be precise with our numbers. And then we have x is 1/2 AT squared plus V0t plus x0. Acceleration is 0. Initial velocity is 15.58 t. And the initial position is 0. So just like the last problem, we have the same equation, 15.58 t. And 15.58. So the x didn't change. It's the same. What is going to change Let's see if our z changes. Acceleration is minus 10. The initial velocity is still 9 in the vertical direction. So this equation is the same. And z is 1/2 at squared plus v0t plus z0. Acceleration is minus 10. Initial velocity vertically is 9. And z0 is 0. So we have the position of the ball is minus 5t squared plus 9t, which is also exactly the same equation. And now the position of the ground, instead of being 0, is now minus 100. So this is where we can go to Desmos, do our calculations to find this intersection that will give us this time, which we will then plug into our VZ, and we can also plug into our X. So you might want to pause here and do this sample calculation to practice yourself. So after doing our Desmos, we should have gotten 5.462 seconds, which to two significant digits is 5.5 seconds. If we compare that to our table, whoa, that's exactly what we said when we estimated. Pretty good. We plug in that time to our VZ and we get minus 10 times 5.462 plus 9. So minus 54.62 plus 9. And that is minus 45.62 meters per second. 45.62 meters per second. Let's see how that compares to our VZ over here. Boy, minus 45.62. Minus 46. We did pretty well there. And now we want to know the X displacement. X equals 15.58 times 5.462. And you may want to do that calculation on your own to practice your fluidity with Desmos. And you should see that you get 85.098 meters. And if we check that, 85, so we were off by a little bit, but 88, we were pretty close, plus or minus 3. And so we now have all of these facts that we're looking for. All right, so how long will it take to hit the ground? Exactly 5.5 seconds. We were spot on. The base of the cliff, well, not 88, but 85 meters. Horizontal and vertical velocities, well, 15.58, we were good. And with minus 46, we said it was going to be minus 46. We were spot on. And what will the impact velocity be? Well, just like we did before, we've got to draw this out. And I don't suspect we're going to get a noticeably different answer, given the significant digits that are in play. But we've got 15.58 minus 45.62. And if we're looking for this angle phi, so we've got c squared equals a squared plus b squared. C is the square root of a squared plus b squared. And we have tan theta equals opposite over adjacent. Theta then is the inverse tangent of opposite over adjacent. And that gives us the square root of 15.58 squared plus 45.62 squared. And the inverse tangent of 45.62 over 15.58. And again, this is an opportunity for you to practice with your Desmos. And you should get, in this case, that the resultant velocity is 45.79 meters per second, which to two significant digits is 46 meters per second, which is exactly what we got from the table. So being more precise didn't help us in this case and give us more significant digits. And we find that phi is 71.14, which is 71 degrees. And as we look at the previous example, we had 71 degrees as well. So it gave us nothing different by using the precise numbers, which is pretty amazing. Just pretty amazing. Now, the last step we would do here is to just take a look at the graphing of these. And I'll first do the x graphs. So let's first take our VT graph. And let's see here, our OA Zerga, make sure we are being diligent here. Origin right there is 0, y-axis is v, x-axis is time. The intercept at time 0 in the x direction, the velocity was 15.58. So v0 equals 15.58 meters per second. All right, and what can we read off this graph? Well, we can read the velocity in time, and the gradient is delta v over delta t, which is the acceleration. In this case, the acceleration equals 0. There was no acceleration in the x direction. In the area, v times t gives us the displacement, delta x. So our curve that shows zero slope looks like this. And when we examine the area, we see that in equal times, we get equal displacements, like so, with each successive unit of time. When we go to the xt graph, we'll do our OI Zerga again. OI Zerga. Origin is 0. There we are. The y-axis is position in meters. X-axis is time in seconds. The intercepts. Okay, so at time 0, what was the x? Well, the x position at 0 was 0. So x0 equals 0. That's what we saw. And let's see. Okay, so that's our x-intercept. What can we read? X and t. The gradient is delta x over delta t, which is the velocity. And the velocity was constant. The velocity was constant. And the velocity was 15.58 meters per second. So we are looking at a straight line, positive straight line with a constant slope. The slope is the average or constant velocity, which is 15.58 meters per second. And the area, in this case, x times t, has units of meter seconds, which isn't anything we care about. So that is, in the x direction, what our functions look like. In the z direction, we have our vz equals at plus v0. Oh, wait a minute, we're just doing the graph. So we have vz and t, our OI Zerga. Origin is there, 0, y-axis vz in meters per second, x time in seconds. The intercept, okay, in the vertical direction at time 0, the velocity was 9. v0 equals positive 9. Now remember, the velocity decreased, and it eventually got to be 0. So it decreased to 0. And now that's our x-intercept. So this is the time at which v equals 0. And so those are our intercepts. What we can read is velocity in time. The gradient is delta v over delta t, which is the acceleration. And it's gravity causing us to accelerate, so it's minus 10. We should have a negative slope, and it stays 10 throughout, so it should be a straight line whose slope is minus 10. The area is v times delta t, so that's meters per second times second, so meters, and that's delta z. So delta z, if we look at the area in this case, all right, so that's delta z in its positive area. And then this is going to be negative area. And it's at this point that these areas are equal to each other. And so that means that at this point it returns to ground height. So the x-intercept is where the velocity is 0. Twice that time is when it returns to ground height, and then the net displacement is 0. And then what we know after that is that this remaining area, whenever it hits the ground, that area must be equal to minus 100, that purplish or that magenta area. So that's our VT graph. Our ZT graph so Z and T, and the Z is in meters, and the time is in seconds, and we always ergo this thing. Origin 0, we got that. Both are 0. Y-axis, good. We got that. X-intercepts, okay. So at time 0, what was the Z? Well, it was 0. And at some point, it got to its maximum height. At an equal amount of time after that, it got to the same height. And then at some point later, it got to minus 100. So we see a downward cupping parabola. And if you remember, our equation for z was z equals minus 5t squared plus 9t. The negative means it's got a negative concavity, or the parabola cups downward. So what can we read from this graph? Position in time, the gradient is delta z over delta t, and that is the velocity. And if we look at the velocity, it's big. It gets to be 0 right there, so the velocity is 0. It's negative now, getting faster, faster, and faster. So at this point, we've got a slope which is equal to minus 48, I think it was. In the area, in this case, meters times seconds, tells us nothing of consequence. So that's how we could use our average velocity table, our analytic solutions, and our graphs to understand, analyze, and connect the concepts related to a two-dimensional projectile launched off a cliff.